Okay. Let's start the first lecture in Introduction to Information Science and Engineering. The first topic is Basic Structure of Computers and Programming. In this class, you should submit a report at the end of each lecture. If you are not in this room, download this template, fill in by handwriting while watching this video. After you finish the report, take photo and send by email. Also, you can ask questions by email. The automatic receipt will be sent back within 5 minutes. The outline of this class is here. Today we focus on the overview of von Neumann computers. But keep in mind von Neumann computers has lowest power efficiency, and has no room for getting high speed due to physical limitations. Don't misunderstand, just studying normal computers is sufficient for your future job. The second lecture focuses on non-von Neumann computers for getting high speed and low power. The third and fourth lectures cover the operating system to make computers easy to use. The fifth and sixth lectures cover the software to translate algorithm to hardware. The last 2 lectures summarize the algorithm to solve specific problems. Okay. Let's start the first topic. Here you can see the goal of today. If you cannot answer these questions, you should be ashamed as a master of information science. Here, you can see 6 basic ideas to design high-speed computers. The first one is pipelining to speed up the frequency. The second one is superscalar to increase the performance without higher frequency. The third one is vector processor for high-performance numerical programs. The fourth one is VLIW, similar to superscalar but more power efficient. The fifth one is multithreading for efficient use of hardware, and the last one is latest technique for non-von Neumann computers. All of these ideas were introduced around 40 years ago. We can see many kind of computers. But every computer can be classified by the combination of 6 ideas. For example, the combination of pipelining, vector processor, and multithreading leads to GPU, and the combination of pipelining, vector processors, VLIW, and multithreading leads to a supercomputer, what we call VPPI, developed 30 years ago. The latest idea is systolic array that Google employs in TPU, and the leftmost 3 computers are variations of non-von Neumann computers in my laboratory. If we need more powerful computers, the only thing what we can do is just connecting many computers with some kind of network like this way. We have 2 different kinds of multiprocessors. The first one is multiprocessor system that has single memory space and is controlled by single operating system. The example is your desktop PCs. The second one is also multiprocessor system, but each CPU has its own memory space. This means one operating system is running on each CPU. Where can we see this kind of computer? The example is powerful supercomputers such as K-computer, Fugaku, and cloud system. The difference between the shared memory system and the distributed memory system will be presented in other class. Okay. Let's focus on CPU. As you know, CPU is the only platform for programmers who can write only C language. The rest of this lecture provides minimum but important knowledge for such kind of programmers. For getting more knowledge on platforms, you can join other class high-performance computing platforms. The first step is understanding basic structure of computers and programming. You often use complicated data formats such as floating point number to represent the real world. The computers should manage any data with some combination of different kind of transistors. The fundamental element is imperfect PMOS and NMOS. PCH and NCH are models of PMOS and NMOS. When the gate is low, PCH can pass high voltage. When the gate is high, NCH can pass low voltage. In this case, the output level is inverse of the input. The pair of PMOS and NMOS is called a Cmos Gate, and this circuit is represented as an inverter. But we need 2 input Cmos gates to build a calculation unit such as adder, multiplier, and divider. The left side is a NAND gate. The output is low only when both of the inputs are high. The right side is a NOR gate. The output is high only when both of the inputs are low. By combining many number of logic gates, we can build an arithmetic unit. Around 5,000 of transistors are required for a 2-input 32-bit adder. The basic units of hardware are very simple. The major components are ALU arithmetic and logical unit for calculation, flip-flop for storing 1-bit information, register file for storing multiple 32-bit, 64-bit or more bits, RAM for storing huge data, and CHEM for searching information in memory. The basic components are connected like this way. The ALU, the register file, small RAM and CHEM are integrated in a CPU. But the size of RAM in CPU is quite small, then we need to attach huge external RAM to CPU. And also, some I/O devices are attached to these units. The important points are small memory can operate in high speed, but large memory is slow speed. Now, what is computers? What is the difference between computers and other electric devices? Computers should have some programmable component. The typical flow to run programs on computers includes writing source code, compiling the source code, and invocation of the binary code. Typical compilers invoke 4 components such as preprocessor, generator for assembly code, assembler for object code, and linkage editor for executable binary file. In general, C language is independent from the architecture of CPU. But assembly language depends on CPU like this way. Specific compiler should be used for specific CPU. After the compilation completes, we can invoke executable binary file. A program loader in each operating system reads the file from HDD, SSD, or network, and puts the machine instructions into predefined location in main memory of the system. Also, the loader puts the data into other location in main memory. The left side is CPU including ALU and register file, and the right side is main memory. CPU starts to get the first machine instruction from the main memory, decode the instruction, and execute by using ALU step by step. In this program, the first load instruction is located in address 1000. When CPU gets a load instruction, CPU extracts the memory address from the specified register, accesses to address 2000 in this case, reads 234-5228, and writes it to register A. After the execution of the first instruction is finished, CPU starts to get the next instruction located in address 1004. The third instruction is for comparing register A and B. If A is lower than or equal to B, CPU jumps to the instruction located in address 1xxx. Otherwise, the instruction in address 1010 is executed, then the contents in address 2000 is stored to address 2054 though register A, and the contents in address 2054 is stored to address 2000 through register B respectively. This program can sort the data based on the values. Now, let's see the detail of machine instructions. We have many kinds of CPUs, but the basic instructions can be classified into 3 types. Memory instructions are for moving data between main memory and registers. ALU instructions can execute addition, subtraction, multiplication, and division. In addition, ALU has some logical operations such as AND, OR, exclusive OR, bitwise shift operations. Control instructions are for managing conditional branch, loop structure, subroutine call, and so on. The detailed instructions are like this way, and you can see many options to convert many types and lengths of data to fit to the source data of succeeding instructions. For example, assigned 8-bit data in main memory can be loaded by load signed byte instruction. The length is automatically changed to assigned 32-bit value, then ALU can perform addition with other 32-bit data. Now, you can start to connect C programs to machine instructions. The first line of this source code prepares an array R1 with 100 elements, and the second line prepares an integer value R2. The third line describes the operation just to add 8 to the second element of array R1. The last line subtracts the element specified by R2 from previous result, and update the same location. The compiler generates 6 machine instructions. The first load instruction calculates the memory address of the second element of array R1 by adding register R1 and 4, accesses main memory, and writes the data into register R4. The second add instruction calculates R4 plus 8, and writes the result into register R8. The third instruction stores the value in R8 into the main memory located by R1 plus 4. The rest of the instructions are also combination of load, subtraction, and store. Like this way, von Neumann computer repeats instruction decode, register read, execution, memory access, and write back to registers. We have two different kinds of instruction set. The one is RISC already mentioned. The other is CISC that can get source data for calculation directly from main memory like this way. The first instruction in CISC instructions can access main memory and store the result of addition into register R8. Only two instructions are required to perform each of these C statements. CISC can reduce the size of instructions. However, the hardware is more complicated than RISC. Which one is better? In the past, the price of main memory was quite expensive, then engineers need to reduce the total size of instructions. At that point, CISC was better. However, after the cost of main memory is reduced, we have a chance to employ more memory and increase the performance. RISC was suitable for getting higher clock speed and reducing the size of CPU. The optimal point is always changing according to surrounding technology. If else statement and for statement are also translated with branch instructions. The left side compares the value of x and y by subtract instruction. If x is less than y, the next instruction is changed to label 1 at the top of statement number 1. Otherwise, the next instruction is the top of statement number 2. Loop structure in the right side is also composed by compare and branch instructions. As for main memory, you should pay attention to endian. When you send or receive data in Internet, you should follow big endian. Some major CPU architectures such as IBM and SPARC employ big endian in the left side. However, most of the recent CPU architectures including Intel and ARM employ little endian in the right side. Let's assume some calculation in the little endian system generates ABCD in a register. The data is stored in memory and sent to Internet. The byte stream becomes D, C, B, and A. But correct order is A, B, C and D in Internet. Before sending data, you should change the byte order. Endian is often a pitfall when you write some network program. OK. Let's try the first question. OK. The second question is how to change the byte order. This program initializes I and j to 0, and repeats adding 2 to j 10 times. This is an answer to the first question. I is mapped on register R1, and j is mapped on register R2. Subtract instruction is for checking the loop is finished or not. Adding 2 to j is performed at label 1. Check whether your answer is correct or not. I guess most of the students wrote similar answer. But, if you have some experience on compiler optimization, the next answer is optimal because the result is always 20. If you have an environment to compile this statement, you will see the same code produced by the compiler. This is an answer to the second question. Little endian computers such as Intel PCS and ARM platforms should change the byte order when the data is sent to other computers though network. OK. The basic structure of computers has finished. Let's move to the next topic entitled Memory Space, Stack and Buffer Overflow. For understanding how buffer overflow attack succeeds, instruction level knowledge is mandatory. You have to know how function calls are performed first. Function call is a mechanism to reduce the size of machine instructions. When CPU decodes branch and link instruction, the succeeding instructions are switched to the top of the target function. When the execution of the function is finished, the succeeding instructions should be just after the branch and link instruction. To restore the address of next instruction, branch and link instruction saves the next address into specific link register. Branch exchange instruction located at the end of function reads the link register and restore the address of the next instruction. If the function does not call other function, the address saved in the link register is not destroyed. However, the link register should be saved to main memory, if the function has nested function call. To manage the link register and other registers, systematic procedure to save and restore registers should be considered. This figure shows how to manage many functions. Let's assume a program has main function and several functions in instruction space in the main memory. Each function needs to have some free registers and memory space. Figure A is the case each function has its own static and dedicated memory space. The memory address used in load and store instructions are simply predefined. However, we have enormous number of functions but the memory space is limited. This scheme can be applied to specific small system, but is not for general purpose system. Figure B is the case each function has its own memory space that is allocated dynamically when the function is called. In this way, all memory addresses should be fixed before executing the function, then the speed is sacrificed. How can we eliminate the overhead? The answer is in figure C. Just changing the expression of the memory address from absolute address to relative address, that is a combination of base address and offset, can eliminate the overhead. This base address is called a stack pointer. When a function is called, the dedicated memory space is allocated just by decreasing the value of stack pointer. Let's see the procedure how registers and memory space are managed before and after the function call. In this figure, upper side is memory space, and lower side is registers. Register R0 is for some global value, and registers from R1 to R5 is workspace for each function. Register R6 is the stack pointer, and register R7 is the link register. In figure A, the value of stack pointer is P, the return address is stored in the local space for function 1, and function 1 is running. Figure B shows the status just function 5 is called by branch and link instruction. The registers from R1 to R4 have parameters passed from function 1, and the link register is updated to the return address in function 1. In figure C, stack pointer is changed to Q to open local memory space for function 5, the registers from R5 to R7 are saved to the local space, the return address is stored in the local space, and function 5 is running. When the execution of function 5 is finished, the return value is stored in register R1, the original values are restored from the local space to register R5, R6, and R7, and the stack pointer and link register are restored. By executing branch exchange instruction, that is the final instruction in function 5, the program returns to function 1. In the C programs, most of the return values are stored in register. However, C language permits to return multi-word data. In this case, the return value should be passed through local memory space. In this figure, structure S is an array with 100 integer elements. Function 1 calls function 6, and the function 6 returns the whole of the values in structure S6. Function 1 receives the data and stores in structure S1. In this case, function 1 should prepare local memory space for receiving data from function 6, and provide the top address of the space as a parameter in advance. The address is called hidden argument and should be passed through register R1. In figure B, when the execution of function 6 is finished, the return value is stored in the memory space specified by the hidden argument. In figure C, function 1 copies the return value to the structure S1. The important point is what happens if the length of return value recognized in function 6 is larger than that in function 1. It may happen when function 1 and function 6 are developed by different programmers. If the local memory space in function 1 has only 100 words, and function 6 stores 200 words, the return address saved in the neighbor space will be corrupted. Corrupted return address will be restored to register R7, and branch exchange will start unknown instructions in unknown address. This case is a hint how buffer overflow attack succeeds. We have to consider the way to protect the return address saved in the local space. If we can check the length of the space, the return address can be protected. Upper instructions are normal case, and lower instructions are for checking the length. Safe main has an unimplemented instruction just after the call instruction. The length of the hidden argument is embedded in some field in this instruction. When safe sub is called, the length can be checked by loading the instruction specified by link register. If the length is the same value as expected, safe sub can continue the execution of instructions, and return to safe main by branch exchange instruction with the link register +4 to skip the unimplemented instruction. What happens when safe main and normal sub are combined? Normal sub returns to the unimplemented instruction, and hardware can stop the execution. In the case that normal main and safe sub are combined, safe sub try to check normal instruction, and the length may different. Okay. Now you are ready to understand the mechanism of buffer overflow attack. Function 7 in the left side has a buffer for receive at most 80 characters from keyboard or network. The programmer may assume 80 character is enough to save the name of a customer. However, no one can stop someone types in more than 80 characters through gets function. The return address will be easily corrupted. If some malicious user knows this vulnerability, he or she can send data including some branch target address just fit to the area for saving return address and some malicious instructions for sending back personal data such as password or credit card information to the hacker. The right side is a safe program. The programmer can use fgets and specify the maximum length of data to receive. I guess you understand what we should do for writing safe program. It is important not to use functions that receive unlimited data into local memory space. Here you can see an example. When you compile this code, you have a warning like this way. Also, when you invoke the program, you have warning again. If the length is smaller than 10, this program can reach to the end of the code. However, if the length is larger than the size of the buffer, you will see segmentation fault. This means the function could not go back to the main function. In the case of safe program, you have no warning, and the program can finish the execution with any input. Of course, we have another programming environment that fundamentally has no such kind of risk. This is the overview of memory structure in Java Virtual Machine. In Java Virtual Machine, the memory space for I/O and the stack frame are separated. In this environment, the return address is protected. The programmer can get data from network only to memory space allocated in the heap area. But why Java Virtual Machine cannot replace the traditional environment? From the view of safety, normal CPUs should be deprecated. The reason is in the trade-off between the safety and the speed. By putting the local variables and return address into the same local space based on the stack pointer, the cost for allocating and releasing of the local space is limited to executing only one instruction that changes the stack pointer. However, in the case of Java VM, allocating and releasing of the local space is controlled by another mechanism such as heap management, including time-consuming garbage collection. Now, the security issue is finished. Final topic is cache memory and execution speed of programs. Let's see the memory hierarchy in modern computers. You can see level 1 cache, level 2 cache, and level 3 cache between CPU and the main memory. Around 40 years ago, 8-bit CPUs are directly connected to the main memory, and takes only several cycles to get data from the memory. However, the speed of CPUs was improved faster than the speed of memory. Modern CPUs take more than several hundreds of cycles to get data from main memory. For alleviate the memory bottleneck, small but high-speed memory, what we call cache memory, was attached. If you write programs that access only 32 KB data, your program can run in full speed. This is the same as the size of main memory in past 8-bit computers. In other words, cache memory should be equipped just because the programmers want to use larger memory space than 32 KB. Let's assume you have finished to write a program, and your colleague also has finished the same program. What happens if your program takes 1 hour before the output is generated, but other program based on the same algorithm takes only 1 minute for the same output? You should imagine the reason why your program is running in so slow speed, or you will be fired. One popular reason is due to the poor skills on arranging the memory access patterns to make full use of cache memory in the program. But the cache memory is not almighty. In general, programs have spatial locality and temporal locality. The cache memory can rescue the speed of programs that have sufficient locality. However, if your program generates random access to the main memory or sweep the whole of the memory space, the CPU significantly slow down. Even if you successfully write a program with sufficient locality, the speed depends on the compatibility with the cache hierarchy of the target system. When you plan to buy a new computer, the hierarchy of the cache system should be checked by yourself. This is overview of the history of cache system. Figure A is a simple cache for reuse only. But if the delay time is increased, on-demand data transmission from main memory to cache is insufficient to cover the delay time. Figure B has advanced cache that can start prefetching before the address is accessed by CPU. Figure C has multiple prefetching mechanism and many memory buses to overlap many memory requests. Thus, the power consumption of computers has been increased. As mentioned in the beginning of this lecture, each load instruction generates a memory address. Before sending the address to the main memory, some fields in the address are extracted and used as a key, a block number, an index to the cache memory, and an offset in the cache line. Left side is direct map cache. A cache line is specified by the block number and the index. If the value in the tag memory is equal to the key, the data in the cache body is used with no access to the main memory. In this case, other three cache blocks are not accessed, then the power consumption is reduced. Right side is four-way set associative cache. 4 cache lines are specified by the index. If one of 4 tag memories is equal to the key, the data in the corresponding body is used. In this case, all blocks are accessed. The hit ratio of the cache is a little bit higher than direct map, but the power consumption is 4 times larger than direct map. We have trade-off between performance and power also in cache memory system. Cache memory system can be classified by how store instructions are managed. One is write-though cache. In this case, store data is always written to the cache and the main memory. But basically, the speed of the main memory is slower than cache. A store buffer to balance the speed is mandatory, and if the buffer becomes full, the CPU slow down. When valid data for a load instruction is not found in the cache, related cache line should be replaced with the data from the main memory. Old data in the cache line can be discarded anytime because the main memory has always latest data. The other is write-back cache. In this case, store data is written only to cache, and written back to the main memory later. Note that M-modified bit attached to each cache line is set to 1 when valid data is stored only in the cache line. The cache line replacement procedure is complicated, but the traffic on the memory bus can be reduced. Modern CPUs that have many cores are equipped with this kind of cache memory. Let's consider how cache lines should be replaced in the case of write-back cache. Let's assume store to address A misses the cache, and corresponding cache line has valid data for address B. If M is 0, the cache line has the same value as in address B. The cache line can be discarded. If M is 1, the cache line has new value and main memory has old one. Before discarding the cache line, the new value should be written back to the main memory. Now you are ready to understand how the data should be arranged. In the case of one-dimensional array, the distance of elements is the same between C language and Fortran language like this way. However, in the case of two-dimensional array, the distance is totally different. Let's see two programs that initialize the value of two-dimensional array. One is written in C language and the other is written in Fortran language. In the case of C language, the data that has the same left side index is grouped and located in contiguous address. In the case of Fortran, the data is grouped by the right side index. This means, in the program, innermost loop should count up the right side index in C, and count up the left side index in Fortran. If you have a chance to write a C program based on old Fortran program, you have to exchange the index to keep the execution speed. Let's compare the execution speed of a sample program. In the left side program, the innermost loop counts up left side index. In the right side program, the innermost loop counts up right side index. Which one is faster? The answer is right side program. Around 20 times faster than the left side program just by exchanging the index. Here you can see the summary of today. If you cannot answer these questions, you should be ashamed as a master of information science. Okay. After you finish the report, take photo and send by email. That's all for today.